All right, so this is the last video of the year. This is the last new thing you learn all year. So let's get at it. All right, so this would have been your do now if we were in-person learning, but obviously we're not in-person learning, so probably use it as a warm-up, reminding yourself how to evaluate definite integrals and how to evaluate indefinite integrals. You will need both of those skills today, so possibly pause your screen and then come back at a later point in time so that you can see, oopsies. There we go. There's the answers, and you can actually see I have some work on number 1 showing how to do the U substitution on that one. Not the U substitution, sorry, the U substitution is in number 2, reminding us how to do the U substitution in number 2. There. So moving on a little bit. Section 8.4, improper integrals. Until now, you've been finding integrals of continuous functions over closed intervals. Sometimes we can find integrals for functions where the function or the limits are infinite. Those are called improper integrals. Improper integrals, just to again emphasize this box right here, any integral involving infinity anywhere you have, it's called an improper integral. So definition of improper integrals from the book, you actually have if x is continuous on the interval from a to infinity, then the integral from a to infinity of f of x dx is equal to the limit as b approaches infinity of the integral from a to b of f of x dx. If f of x is continuous on the integral from negative infinity to b, then the integral from negative infinity to b of f of x dx is the limit as a approaches negative infinity of the integral from a to b of f of x dx. And if f of x is continuous on the interval from negative infinity to infinity, then the integral from negative infinity to infinity of f of x dx is equal to the integral from negative infinity to c of f of x dx plus the integral from c to infinity of f of x dx, where c is any real number. Basically, what all of this stuff says, and I know there's a lot of words there, but all it says is if you have an integral that involves infinity as either the upper limit, the lower limit, or both, you need to rewrite the integral as a limit because we can't actually plug in infinity. We need to think of it as a limit. All right, so what we have here is we have 2 possibilities for an integral. One, you can get a number out of it. Let me get myself up here. So one, you can get a number out of it, and we call that convergent, meaning the integral has an actual finite value. You also have another option where you do not get a finite value, where you get infinity. That option is called diverge. So converge, you get a number for the integral. Diverge, you get infinity for it. So you may be saying, how is it possible for an integral going up to infinity to be a finite value? Well, let's look at one right here. I don't know if this converges or diverges yet, but I'm going to show you the process that we go through in order to evaluate if it converges or diverges. Just real quick to illustrate what this expression means. Again, that expression, in case you can't read it, is integral from 1 to infinity of dx over x. What that is trying to illustrate to us is the area under the curve 1 over x. So here I'm just drawing the first quadrant since we don't care about negative x values. If you don't remember what the curve 1 over x looks like, graph it on your calculator, you'll see it. From 1, having our limit right here, all the way up to infinity. So we want to color in this space. All the way as far as we can go, all the way ad infinitum. So one thing that we have to look at here is in order for a function to possibly converge, I'm not saying that this converges for sure, we should make sure that as we go out to infinity, the function gets smaller and smaller and smaller. So one thing that we have to do, something that I informally kind of check every single time, is is the limit as x approaches infinity of the function equal to 0? If this does not equal 0, it means it's going to be either getting bigger or smaller, and therefore we cannot have a convergent area. Now, in order to find out if this converges or diverges, I recognize immediately that this is an improper integral because I have the infinity right here. I know on the previous page there were a lot of A, B, and C and all of that stuff. I don't worry about the variables. Usually what I do whenever I'm doing a problem like this, I just use the variable b. So I'm going to call the limit as b approaches infinity of the integral from 1 to b. And I don't care whether it's the negative infinity or the positive infinity again. I just use this variable. It's just a placeholder. The one variable you can't use in this situation for whatever you're saying approaches infinity, you can't use x because it's already in the problem, right? So now we want to evaluate this definite integral like we've evaluated every definite integral from chapter 5 onward. We want to, limit carries over, so we're not doing anything with that limit as b approaches infinity. We're just looking at b as some number. We'll plug in later. We want to find the antiderivative of dx over x, and we've done that a bunch of times. We know that it is ln of, we don't need the absolute value since we're only dealing with positives, from 1 to b. All right? So we've got the limit as b approaches infinity of evaluate ln of x from 1 to b. So we go down here and we just plug in. We've got the limit as b approaches infinity of ln. We have to evaluate at the upper and subtract evaluating at the lower. Ln of b minus ln of 1. Well, I happen to know that ln of 1 is 0. All I'm dealing with here is what is ln of infinity. We know from last class that ln does increase ad infinitum, so it does get bigger and bigger and bigger. It just does it slowly. So regardless of whether it's getting slowly to infinity or it's getting quickly to infinity, ln of b is still infinity. So this answer is infinity. So what we say, therefore, the integral from 1 to b, the integral from 1 to infinity of dx over x diverges. Why am I writing in lowercase? I never write in lowercase. So again, if our answer ends up being infinity, the function diverges. So I know that's not that surprising. Again, we think it goes on forever. It's got infinite length, so it would make sense that the area would also be infinite. Now I'm going to show you something that I think is super cool. It's what I call party trick math, and it's something called Gabriel's horn. And Gabriel's horn is produced when we take this function, take the function y equals 1 over x, and we rotate it around the x-axis. So this brings in the concepts that we talked about last chapter. So here we have 1 over x, and we're going to rotate it around the x-axis. So when we rotate around the x-axis, we remember that we draw the reflection, and then we start drawing in our cross-sections there. Rotational cross-sections, again, means that we have circular cross-sections. So what this is going to end up looking like, this is going to look like a horn. Like one of those really long trumpets. If you watched the World Cup a couple of years ago, it looks like one of those vuvuzelas. I think I'm saying that right. I'm not really sure because I'm not a sports person. But it's like just a really long horn. And again, this is going to go out to infinity. We're actually going to use the same limits from 1 to infinity. But before we use those limits, we can actually draw our cross-section. So our typical cross-section, seeing that the radius goes vertically, we can see our cross-section is going to be a circle with our radius equal to the y-coordinate. So the area of our cross-section is going to be pi times our r, which is 1 over x squared, which is just going to end up being pi times 1 over x squared. Just using my algebra 2 skills to get that the 1 over x squared, you square 1, you get 1, square x, you get x squared. All right? So we're going to calculate the volume of Gabriel's horn. I forgot that I didn't put up my smartboard here. That's probably going to be nice for you guys to see. So here, we're going to find the volume of Gabriel's horn. And Gabriel's horn goes from 1 up to infinity. And we're just going to take the integral of pi times 1 over x squared dx to produce the volume of that three-dimensional solid. Now looking at this, I see a pi. I don't want to deal with pi, so I'm just going to throw it out in front. I can put a constant multiple wherever I want. It can go outside of the integral. It can even go outside of the limit that I now need to introduce because one of my limits is infinite. This is, again, bringing us back to the improper integrals territory. So we're going to have pi times the limit as b approaches infinity of the integral from 1 to b of, now 1 over x squared, we know in order to integrate that, we want to call it x to the negative second dx. So a couple of things that I'm doing in this step, I am limitizing my limit so that I don't have to direct substitute infinity because that's impossible. So there's where the limit comes from. I'm moving pi in front of the integral and in front of the limit because it is a constant multiple, and I am rewriting the 1 over x squared as x to the negative second, again using algebra 2 skills, and also because I know that I'm going to have to integrate it. Actually, speaking of which, I'm going to have to integrate it now. So I've got pi, limit as b approaches infinity of, now I'm going to take my integral just like it did here, but now since I don't have a power of -1, I have a power of -2, I have to use the power rule for n not equal to -1. So I'm going to add 1 to -2, I'm going to get x to the negative first, and I'm going to divide by my new exponent. So I get x to the negative first divided by -1. And again, we're running from 1 to b, just carrying over my limits to right over here. All right? So now I'm going to sub in. When I sub in, pi hangs around. Limit as b approaches infinity hangs around. Now all we are doing is we are plugging in b, we are plugging in 1. While I plug that in, I'm going to rewrite x to the negative first over -1 as -1 over x, just because, again, I know how exponents work. So looking here, I'm going to have negative, what was my upper limit again? B. Okay, so -1 over b minus -1 over, what was my lower limit? 1. Okay. So now I'm on the step where I have to evaluate my limit. I have the limit as, sorry. I forgot my pi. I want that constant multiple hang around there. So we got pi times limit as b approaches infinity. Well, 1 divided by infinity, any finite divided by infinity is 0. Plus 1 divided by 1 is 1. So what happens with Gabriel's horn when we take this infinite area around, and rotate it around the x-axis, we actually produce a finite volume, which is pretty freaking cool. So what we would say here, just to bring it back to actually the subject that I'm trying to teach you, not just some what I would refer to as party trick math, we would say the integral that we were evaluating, integral from 1 to infinity of pi times 1 over x squared dx converges. And whenever an integral converges, we want to say what it converges to, because that's pretty important as well. It converges to pi. I should say we want to say what it converges to if we can evaluate what it converges to. There are some integrals that we just can't evaluate, so you'll see those later. All right, that's pretty freaking cool. Again, party trick math. Fun stuff. Here's another improper integral. It's not as impressive as Gabriel's horn. You do it the exact same way. Anytime you have a limit that is infinity, again, since we can't limitize, or since we can't d-sub with infinity, we need to limitize the limit. So we're going to have limit, and again, I don't care what variable you use as your limit variable there, as long as it's not x. I guess in this case, we also can't use e, we can't use d. Any letter that exists in the problem, you can't use it. Integral from 1 to b of e to the negative x dx. Once we get here, this becomes just a definite integral problem. We have, let's see, limit hangs around of antiderivative of e to the negative x. Well, I know that the integral of e to the x is e to the x, but I have that chain of -1, so I'm going to have negative e to the negative x running from 1 to b. And again, at this point, I don't care that the limit's hanging out there. I know it's intimidating. We're going to deal with that when we have to deal with it. That's not yet. So we have limit as b approaches infinity. Stick that off to the side. Now we're going to plug in negative e to the negative b minus negative e to the -1. All right, so now we've done most of the problem. We have integrated. The only thing we haven't dealt with is the improperness of the integral. So now we need to evaluate the limit. And to evaluate the limit, probably the easiest way to do this one is to recognize e to the -b actually means 1 over e to the b. You might be able to do that part in your head. I'm not really entirely sure, but that would go on in my head, and then I would put my answer down, because all I'm trying to recognize is I now have infinity in my denominator, and anytime infinity is in my denominator, as long as finite is in my numerator, I get 0. So this is going to be 0 plus 1 over e. That's just going to give me 1 over e. And there I'm done. So this function converges to 1 over e. Since the directions do not say, does this function converge or diverge, I don't have to say it converges to 1 over e. Me saying that the integral from 1 to infinity of e to the -x dx is equal to 1 over e implies that the integral converges. So this one, it's all about reading the question. Let's see, do I have another one? Do I have another one? Oh yeah, I do. Yeah, I do. Integral from 1 to infinity of quantity 1 minus x times e to the -x. Well, this looks scary, but before we get to scary, let's go here. First step. I don't know anything to do. At least I'm going to get some points, right? 1 to b of 1 minus x e to the -x dx. Okay. Now this becomes difficult. This one, I look at my integral and I'm trying to figure out what the integral is, and I have no clue. So I have to look for more advanced techniques in order to evaluate this integral. From chapter, it was chapter 6, man, so long ago. We know that the next strategy we use is U substitution. So if I was to use U substitution, the only composition I see is that e to the -x, and the other stuff that I have is not the derivative of e to the derivative of -x. So I know U substitution does not work. The next thing that I try is integration by parts. So in integration by parts, I look to see if I have a product of two functions. And indeed I do. I have 1 minus x times e to the -x. Now further than that, I know that I have to choose my u. I'm going to use LIPAT. No logs, no inverse trig. Polynomial. Hey, when I have a polynomial, I know a real easy way to evaluate this integral. Do some scratch work over here. Do some tabular integration. Tabular integration, all I have to do, take derivatives down the first column, so -1, 0. Look at that. The table is only 3 steps long. Integral of e to the -x, negative e to the -x. Integral of negative e to the -x, e to the -x. connects the doodles. We got plus, minus. So now we can actually establish what our integral is. We now have the limit as b approaches infinity of, looking here, I'm going to want plus, but we've got a negative, so it's going to be negative quantity 1 minus x times e to the negative x. Minus negative, so plus 1 times e to the negative x. Rocking it from 1 to b. All right, cool. We're good, we're good, we're good. Now we've done what I consider to be the hard part, finding the integral. Now I'm going to do my fundamental theorem of calculus. Again, don't be intimidated by having a b hanging out here. We don't care about that yet. We'll worry about that when we get to it. We know that we have to evaluate at the upper, so we're going to have negative b minus, nope, negative 1 minus b times e to the negative x. Nope. Why did I put x there? I need to plug in my b. Negative 1 minus b e to the negative b. Okay, there we go. Plus e to the negative b minus, evaluate at the lower, negative 1 minus 1 e to the negative 1 plus e to the negative 1. Do I have enough parentheses there? Parentheses. If that's my only issue, then I'm lucky here. Okay, so I'm going to go through here and clean this up just a little bit. Look at stuff that I don't worry about, and there is one particular limit that I am going to worry about. First off, we went through that last problem where we saw e to the negative b when b was infinity ended up being 1 over e to the b. So I know that this problem, just from the last problem that I do, is 0. So you now know if you have a number to a negative infinite power, that is 0. Looking over here, I've got 1 minus 1. That's 0 times, I don't care what it's times, that's just going to be e to the negative. That's just going to be 0. 0 times e to the negative first is 0. Now looking a little bit further, I can see now I have minus e to the negative first. So I'm just going to keep that outside of the limit, and I'm going to recognize the only limit that I have left here is the limit as b approaches infinity of negative quantity 1 minus b times e to the negative b. So looking there, I'm just trying to evaluate this limit. Limit as b approaches infinity of, I'm going to distribute that negative and get, and get b minus 1, again distributing in my negative, e to the negative b. Now looking at that, I can tell that I now have infinity minus 1 times in e to the negative infinity, 0. Sucks about that is it's an indeterminate form. Sucks that it's not the fractional indeterminate form, because now we need to adjust it into fractional indeterminate form, so we get limit as b approaches infinity of, we look for which one's easier to reciprocate, b minus 1 or e to the negative b. I'm just going to tell you guys that flipping that negative exponent to the denominator very quickly makes it go into infinity over infinity. Since it's infinity over infinity, I know that I can do L'Hopital. We've got limit as b approaches infinity of derivative of b minus 1, 1 over e to the b minus still that e to the negative first. Oh man, this is cool now. I got 1 divided by infinity. That's 0. That goes bye-bye. The answer to this is negative 1 over e. So this improper integral does converge as well. Man, that was tough. That was a tough problem. But you know what they say about tough problems? They're really difficult. Oh man. Oh, whew, whew. This one sucks. Look at this. We got lower limit is infinity. We got upper limit is, lower limit is negative infinity. upper limit is negative infinity, or it's positive infinity. Ooh, I can't even read right now. So looking at this, in order to tackle a double infinite limit kind of problem, what we need to do is split this up into two different integrals. We want the integral from negative infinity to some sort of placeholder. The placeholder that I'm going to use here is just the placeholder that I always use, 0. So we've got the integral from negative infinity to 0 of e to the x over 1 plus e to the 2x dx. Add to it, since I used my placeholder as 0, I need to use my lower limit placeholder as 0 and my upper limit as infinity, e to the x over 1 plus e to the 2x dx. Now we do recognize that since we have two integrals with infinite limits, we have to do two limits here. So we need to limitize both integrals. So we're going to do the integral from, since we're using 2 here, you really could use the same variable there, but it just feels icky when we use the same variable. So I'm going to switch it up. And since this is the lower limit, I'm going to call this limit as a approaches infinity of integral from a to 0 of e to the x over 1 plus, and I'm going to put something up here to recognize that e to the 2x is really e to the x squared, isn't it? Wonder why I did that. Plus limit, and again, you could use the same variable when you limitize these two integrals, but it gets a little bit murky when you do that, and really, you don't want to do that, so I'm just going to use b over here as my limit. 0 to b of e to the x over 1 plus, and again, just noting here that e to the 2x is e to the x squared dx. Okay, so just like last time, this problem scares me in that I don't know what the integral is off the top of my head. So I'm going to look for some alternates for what I'm for how to evaluate the integral. So I start off, okay, I don't know what it is off the top of my head. I go to u substitution. For u substitution, I look for any compositions of functions. Remember when I pointed out that e to the 2x is e to the x squared? That now becomes a composition of functions, with the inner function being e to the x. Well, looking at the derivative of e to the x, oh, look that. E to the x is the derivative of e to the x, and it happens to be in the problem as well. So I know that I'm going to use u is equal to e to the x. Therefore, du is also equal to e to the x dx. One thing to note here is this problem, the u substitution works in both of these integrals. So I'm actually doing work for both of these terms in the ultimate problem. Now we do know that since we're dealing with definite integrals and u substitution, I really want to reevaluate my limits. So I want to find u of 0, my upper limit over here. I also want to find u of a. Looking at u of 0 is going to be, u was e, so e to the 0th power, which is equal to 1. U of a is actually going to be the limit as a approaches, that shouldn't have been infinity over there. I was so distracted with how hard this problem looked. This should be negative infinity over here. Lower limit is negative infinity, this one should be negative infinity. Which leads me to what u of a is. Since we're talking about the limit as a approaches negative infinity, this will actually be the limit as a approaches negative infinity of e to the a. And we know that e to the negative infinity, again from all those problems that we just did, is equal to 0. So my new limits over here become 0 to 1. Over on this side, again, I already have my u. All I need to do is find u of my upper limit, which here we're talking about the limit as b approaches infinity of e to the b, which is equal to infinity. So we're just going to keep it as b. Infinity, since we're not trying to compare infinities, it's okay to leave it right there. Whoopsies. That's not how I spell u. We also want to find u of 0. We already found that. It's 1. So now rewriting my integrals here, I'm going back to blue to demonstrate that I'm still doing this work here. Limit as a approaches negative infinity. Not gonna forget that negative now. Integral from no. Again, we want our lower limit was a. Oh, it's now 0. Okay. 0 to what was once 0 is now going to become 1. All right. Of e to the x dx becomes du. Okay, so du over 1 plus e to the x becomes u. Okay, cool. U squared. All right, nice. Actually, looking at this problem, since the integral doesn't involve a anymore, we don't have to use the limit anymore. We can actually toss out the limit on this particular part of the problem, which we will do in the next step. Plus, limit as b approaches positive infinity of the integral. What was once 0, we want to now make into 1. What was once b, we want to keep as b because we're still talking about infinity. And since I already did all this work where I adjusted e to the x over 1 plus e to the x squared dx, I'm just going to copy it over here. Du over 1 plus. It's not how I'm really failing on how to spell u today. All right, so now I know, again, that first part, I no longer have to use limit. So that first part for evaluating the integral here, I just need to find out what gives me a derivative of 1 over 1 plus u squared. And looking at my derivative sheets, I think we've done this one before. That's arctangent of u. And again, I'm running from 0 to 1. And just a reminder, I dropped my limit notation here because nothing in the integral involves a anymore. So it doesn't matter. Plus, that second one, since I still have b hanging around, we have to have our limit as b approaches infinity. And here we already did the hard thinking, so that's going to be arctangent of u and carry over my limits from 1 to b. All right, cool. We're almost out of the woods. So let's see here. We've got evaluating the first part using the fundamental theorem of calculus. We've got arctangent of the upper limit, so arctangent of 1 minus arctangent of 0 plus forgot my limit notation. Got so intimidated by trigonometry popping in here that I forgot that limit notation. Limit as b approaches infinity. Again, we're dealing with b still being here, so we need it to hang around. Tanb minus, arctanb minus arctan of 1. Now for the fun part. We need to evaluate arctangencies. You could probably plug this stuff into your calculator, but why would you? It's so boring to plug it into your calculator, especially when we know we can use the unit circle. When we're using the unit circle, we know that arctangent only deals on the right side of the unit circle. We know to find arctangent of 1, we need to find out where the ratio of y to x is equal to 1. Well, I know immediately that that's at that point where I have root 2 over 2, comma, root 2 over 2, which is pi over 4. Pi over 4 minus something plus something minus pi over 4. Well, just looking at that, I can see that the pi over 4's are going to go bye-bye. So I've got a positive pi over 4, and I've got a negative pi over 4. But before we get there, I'm looking for where my ratio of y to x is equal to 0. That's wherever y is equal to 0. So looking here, we know that we have 1, 0, where y is equal to 0 is at theta equals 0. Now the hard one, arctangent of where b is approaching infinity. What we're looking for is where do we get an infinite ratio. An infinite ratio is going to happen when you divide by 0. If we look at this point right up here where we have 0, 1, the ratio there would be 1 divided by 0. Now some of you might be saying, why are we not using 0, -1? Because there we have -1 divided by 0. This would be the limit as b approaches negative infinity of arctangent of b. The limit as b approaches positive infinity of arctangent of b is this value right up here, which is pi over 2. So long story short, gonzo, because they cancel each other out, -0 plus pi over 2, this function, or this integral, converges to pi over 2, which is pretty fun. We do still have some other types of improper integrals with infinite discontinuities. Again, improper integrals exist wherever infinity comes into the integral. So anytime you have an infinite discontinuity, you have to use a limit to get around that infinite discontinuity. This one, a couple of years ago when I practiced AP test, this was one of like the 2 problems that I got wrong on the multiple choice because I forgot to check for infinite discontinuities. But integrals of functions that become infinite at a point within the interval of integration are improper integrals. If f of x is continuous on the interval from a to b, then integral from a to b of f of x dx is equal to the limit as c approaches a from the right of the integral from c to b of f of x dx. If f of x is continuous on the interval from a to b, exclusive of b, meaning the infinite discontinuity happens at b, then the integral from a to b of f of x dx is equal to the limit as c approaches b from the left of the integral from a to c of f of x dx. And if f of x is continuous on the interval from a to b exclusive of c, meaning the infinite discontinuity happens at c, then the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Third option there is basically split it up wherever the infinite discontinuity happens. And this can be difficult. So we have to acknowledge where the infinite discontinuities happen. The infinite discontinuities happen when we divide by 0. So looking here, we can see very easily if we're going from 0 to 1, an infinite discontinuity is going to occur whenever the denominator is equal to 0, which is going to happen when x is equal to 0. So that's going to lead me into saying that this is equal to the limit as, and again, some placeholder. I know in the previous page we used c for everything, but again, it just feels right for me to use b. I can recognize it right away. I like using b. I want the limit as b approaches 0, and now in order to determine whether I'm coming from the left or the right, what I put into my head is just a number line. On that number line, I know I'm talking about the interval from 0 to 1. If I'm going on the interval from 0 to 1, I'm somewhere in here, and I want to approach 0 from somewhere in here, which means I need to come in from the right. So this is going to be the limit as b approaches 0 from the right of the integral from b to 1 of, and I know that since I have an x in the denominator and the exponent is not 1 in the denominator, I need to rewrite this as x to the -1/3 dx. Again, that's because n is not equal to -1. Since n is not equal to -1, we use the power rule where n is not equal to -1. So our integral is going to become x to the x to the -1/3 plus 1. So when I do -1/3 plus 1, I'm going to get 2/3. So this is going to be x to the 2/3 divided by 2/3. Notice that when I said divided by 2/3, I changed it to multiply by 3/2. just to make my life a little bit easier. I'm going from b to 1. Now that I've gotten that far, I'm going to use the fundamental theorem of calculus, part 2, which means I evaluate at my upper, 3 times 1 to the 2/3 power over 2 minus evaluate at the lower, 3b to the 2/3 over 2. Now evaluating this, 1 to the 2/3 power, that's 1. 1 times 3/2, I get 3/2 minus, I'm just going to d-sub. Let's see if d-subbing works here. 0 to the 2/3 power. Oh, that's 0. 3 times 0, oh, that's 0. Divided by 2, oh, that's 0. So I can see that this improper integral converges to 3/2. Again, in this situation, you're looking for where does the infinite discontinuity occur. That's what you limitize. Look at the interval to figure out which direction you're coming from, and then proceed as we've done every other problem here. See, do I have another improper integral with an infinite? Yes, I do. I certainly do. I wish I would have gone from the other side, but whatever. We deal with what we have, right? So here we can again see that our improperness occurs at 0. So we're going to have limit as b approaches 0. Now again, I would put the number line in my head, but since you guys can't see in my head, I'm on the interval from 0 to 3. I'm somewhere in here, and I'm trying to approach 0, so I'm approaching from the right. Limit as b approaches 0 from the right. Integral from b to 3. Now again here, since my exponent in the denominator is not the 1, I want to rewrite this as x to the -3rd dx so that I can use the power rule where n is not equal to -1, which just means I'm going to have -3 plus 1 gives me -2, -2, x to the -2 over -2 from b to 3. And again, I see that the x to the -2 over -2, I can convert that into -1 over 2x squared. Taking that negative exponent, just flipping it to the bottom, so that I can write this easily as limit as b approaches 0 from the right. Again, not worrying about that limit yet. We'll worry about it soon enough. -1 over 2 times 3 squared minus -1 over 2b squared. All right, cool. Now we're going to worry about that b value, because I do happen to see that we've got -1/18 plus over here, I know that I'm plugging in 0 down. Oh man, what happens when I divide 1 by 0? 1 divided by 0 is either infinity or -infinity. Since in this case we're dealing with +0, and even we square it to make it even further, +0, 1 divided by +0 gives me +infinity. We've got -1/18 plus infinity. That just means that we have an infinite value, and the way that we say that we have an infinite value is we use the D word. Because we got infinity, the integral from 0 to 3 of dx over x cubed diverges. Period. I think we've got one more concept here. One more concept. I'm going to give you all a p-test. Okay, so p-test occurs when we're talking about the integral from 1 to infinity of 1 over x to the pth. So we're going away from our infinite discontinuities. We're going back to the infinite limits. What happened when we had converge versus diverge when we talk about the infinite limits? We had x to the pth in the denominator. If x to the pth stays in the denominator when I take my integral, then I'm going to have 1 over infinity, which is going to produce a 0. If I make my x go up into the numerator, I'm going to have whatever evaluated at infinity. Since the infinity is no longer in the denominator, I'm going to get an infinite value. And thus I would have a divergent integral. So looking at that, again, just looking at this, the lowest, or the biggest p that I could use that would cause x to the pth to flip up to the numerator is if I have 1 over x when my p is equal to 1. Because when I look at that, let's just limitize and integrate at the same time. Limit as b approaches infinity. The integral of 1 over x is ln of x, which is going to cause, when I have this 1 to b, I'm going to have that ln of infinity. And that's going to work for any number, any p that we have that is smaller than 1. Like if I had the integral from 1 to infinity of, let's just say I had 1 over the cube root of x dx. Well, I happen to know that the cube root of x can be rewritten as integral from 1 to infinity of x to the negative 1/3 dx. So when I integrate that, again, I'm going to get that limit b approach infinity. I'm going to get, when I add 1 to my negative 1/3, it's going to become a positive exponent, which is going to bump that x up to the numerator. So this is really going to become that 3 halves x to the positive 2/3, going from 1 to b. And when I plug in my b here, I'm going to have infinity to the 2/3 power, which is still going to be infinity. Contrast that with if you have a p that is bigger than 1, like let's say I had the integral from 1 to infinity of 1 over, we did this one before, 1 over x squared dx. When I antidifferentiate that one, I have to think of this as x to the negative 2nd. So when I take my integral, I'm going to have, see, negative 2 plus 1 gives me that negative 1. I'm going to have x to the negative 1st, divide by negative 1, running from 1 to b. Looking at that, I now have infinity to the negative 1st power, which gets me that 0. And that's going to work as long as my p is bigger than 1. So long story short, if you have integral from 1 to infinity of 1 over x to the pth, you can save yourself dx. You can save yourself a lot of work just by looking at what the p is here. If p is less than or equal to 1, that means the integral diverges. And remember, when the integral diverges, you ain't got to do anything. You just say it diverges. That means it goes to infinity. If p is greater than 1, then the function is going to, or the integral is going to converge. So that kind of sucks because you would actually have to say what it converges to, but hopefully this is just going to be bundled in some sort of question that says, does this integral converge or diverge? And like, just think about this. If you had the integral from, let's just say we had 7 to infinity of 1 over the square root of x dx. I can see very easily that that is going to diverge. How do I know that that's divergent? Because I look at my p. My p here is the the exponent in the denominator. My exponent is 1/2. 1/2 is less than or equal to 1, therefore this function diverges. Now I know some of you are looking at the fact that this lower limit is 1, where this lower limit is 0. It actually doesn't matter what the lower limit is. In fact, you could actually find out that this is going to be equal to the integral from 7 to 1 of 1 over square root of x dx plus the integral from 1 to infinity of 1 over square root of x dx. You don't actually have to think about that, but what we do know is this value, since there's no infinite discontinuities, the function is continuous. This is finite. This, by using my p-test, is infinite. Therefore, finite plus infinite gives you infinite, and any way you look at it, this function is going to diverge. So what I'm trying to say there is, it doesn't matter what your lower limit is, regardless of what your lower limit is. If you have your p is less than or equal to 1, it's going to diverge. If your p is greater than 1, it's going to converge. Now, it can't be that easy. I'm not going to give you problems where you just p-test it immediately. It's going to be more of a comparison. And this is an integral comparison, an improper integral comparison. I almost called it the integral comparison test. That's a different thing that we get to in chapter 9. So if you let f and g be continuous on the interval from a to infinity, inclusive of a, exclusive of infinity, because obs, with 0 less than or equal to f of x less than or equal to g of x for all x greater than or equal to a, then the integral from a to infinity of f of x dx converges if g of x, if the integral from a to infinity of g of x dx converges, and the integral from a to infinity of g of x dx diverges if the integral from a to infinity of f of x dx diverges. Basically what this is saying is if g is above f, if f diverges, or sorry, if g is above f, if f diverges, meaning f being infinite, g is bigger than it. So g is bigger than infinity. The only thing beyond infinity is another infinity. So if f is infinity, g is infinity as well. G diverges. If g is finite, remember f is smaller than g, that would mean that the integral of f is smaller than the integral of g, and therefore f is smaller than finite. Infinite can't be smaller than finite, so f would have to converge as well. Let me just show you in context how this works. We have the integral from 2 to infinity of cosine squared of x over x squared. We are going to take the integrand cosine squared of x over x squared, and we're going to compare it to a much simpler p-testable function. Now, in order to compare fractions, you have to think of two things. If you increase the numerator, you increase the quantity of the fraction. If you increase the denominator, you decrease the quantity of the fraction. If you decrease the numerator, decrease the quantity. If you increase the denominator, you decrease the quantity. All that gets to say is cosine squared, we know that cosine runs between -1 and 1. So cosine squared has to be less than 1. Since we're saying the numerator is less than 1, the fraction would be less than 1 over x squared. When we look at the integrals here, we're again looking at the integral from 2 to infinity of cosine x squared dx. We're looking at the integral from 2 to infinity of 1 over x squared dx. We're looking at that p-test on that second one. We look at our p. Our p is 2. Is 2 less than or equal to 1? No. Therefore, converges. And I will tell you that this pops up regularly on multiple choice sections of the AP test. So that's why I bring it up here. It's a quick thing that you can just like kind of recognize here. We're looking at the integral. We're looking at the integral from 3 to infinity of 1 over x minus e to the negative x. So 1 over x minus e to the negative x. So we're looking at that denominator. If I can get rid of that denominator, I can make this into p-testable. So I want to take away that e to the negative x. Well, I'm not actually taking it away because there's a minus here. In order to delete it, I need to add on an e to the negative x, which increases my denominator. If I'm increasing my denominator, I'm decreasing the value of the fraction. So this is going to be greater than 1 over x. Again, we're trying to look at the integral from 3 to infinity of 1 over x minus e to the x dx. So we compare it to the integral from 3 to infinity of 1 over x dx. We look at our p-test. Our p-test, this is a 1. 1 is less than or equal to 1. That means this diverges. This is infinity. This is bigger than infinity. So this has to also be infinity, so it diverges. And again, this is called a comparison test. Comparison test, we might say. Yeah, comparison test. We can call it a comparison test. Your last problem here. 1 plus 3 sine fourth 2x over square root of x. We want to compare it to a p-testable function. P-testable function would just be that 1 over square root of x. To do that, we are deleting that 3 sine fourth of 2x. So we are taking away from the numerator. We're decreasing the numerator, which means we are decreasing the value of the function. 1 over square root of x. Again, we're trying to do integral from 1 to infinity of that dx. Integral from 1 to infinity of that dx. P is 1/2, so this diverges. This is bigger than infinity, so this is infinity as well, and it diverges. Woohoo! That was fun. That was fun. Again, this was the last new lesson of the year. So it was a good year, guys. I'll see you tomorrow.